Today we are going to discuss something about organic chemistry, and today's topic is amines. This class is totally for class 12 because amines are in class 12 syllabus. So students, please come and join my class. So what are amines? Amines means the functional group NH2. Amines. Amines as a functional group of NH2. Now amines, when this NH2 is attached to an alkyl group, that is CH3NH2, this is an aliphatic amine, and when this NH2 is attached to a benzene ring, then this compound is called aromatic amines. So amines may be aliphatic or aromatic. First of all, in amines, the nitrogen carries a lone pair electron, and you know the molecules or the compounds which can have lone pair electrons and which can donate lone pair electrons to others are called a base, a Lewis base. So both aliphatic amines and aromatic amines are Lewis base, because in both the cases the atom nitrogen has lone pair electrons on it. Okay. Now the tendency to donate the lone pair electrons is called their basic strength, how easily they can donate their lone pair electrons to others. That is called their basic strength. Now between an aliphatic amines and an aromatic amine, in both the molecules nitrogen contains lone pair electrons. Now let us see which one has the greater tendency to donate its lone pair electrons to others. Now we know that CH3 group has plus I inductive effect. So CH3 due to its plus I inductive effect repels the bond pair electrons towards the N atom. That is why that N gets some excess electron density. Now if when nitrogen gets some excess electron density, it can easily donates its lone pair electrons to others. Okay. So in methylamine, that is in CH3NH2, the electron density on nitrogen atom is increased due to the plus I inductive effect of CH3 group. That is why its donating tendency also increased, and methylamine is a good base. But in case of aniline, the lone pair of nitrogen is in conjugation with the pi electrons of benzene. Now how these pi electrons are present? In benzene hexagonal shape, the double bonds are like this p orbitals, and p orbitals make make lateral overlapping to form a pi bond. Alternative pi bonds are there. These pi orbitals or p orbitals make lateral overlapping to form a double bond, and these two p orbitals make lateral overlapping to form the pi bonds. Okay. Now when NH2 group is present, now nitrogen has also lone pair electrons, and its lone pair electrons this present in p orbital, which is parallel to the p orbital of carbon. So this here a lateral overlapping may also be formed. When this bond formed, this bond has to be broken, because at a time cannot make two pi bonds. Okay. So when this pi bond is formed, this bond has to be broken. That is, we can show this by this manner. When a double bond is formed by using the lone pair of nitrogen, this carbon now has 5 electron pairs, it cannot or 5 bonds that cannot be happened. So this pi bond has to be broken and will be shifted towards the carbon atom. Okay. So this is called resonance. The lone pair of nitrogen can easily get delocalized into the benzene ring through this resonance. How this resonance happens? Nitrogen has the lone pair electrons. That lone pair electrons will form a double bond, and this pi bond will be shifted towards this carbon atom to form a resonating structure. And how this resonating structure looks? NH2, because it has given its lone pair electrons, so nitrogen will carry a positive charge here. pi bond is shifted on this carbon, so carbon will carry a negative charge here and these two bonds remain intact. Now the next resonating structure is this negative charge will be used to form a pi bond with this carbon, and this pi bond will be shifted to the carbon besides it. Okay, so the next resonating structure is like this: double bond NH2 plus double bond negative charge double bond. Okay, next resonating structure, negative charge will form double bond will form negative charge. The same thing happens, the double bond NH2 plus remains unchanged, this pi bond unchanged, negative charge forms double bond forms negative charge. So these are resonating structures of aniline. Now you can see that in all these resonating structures, actually where amine is present, all these resonating structures are present. Actually aniline is the resonance hybrid of all these resonating structures. Now in all these resonating structures, you can see that nitrogen is not carrying the lone pair electrons but carrying a positive charge. It has not any lone pair electron. How can it donate it to others? That's why aniline is a poor base, because though nitrogen, here we can see nitrogen is present and nitrogen should have a lone pair electron, but that lone pair electron is not localized on the nitrogen atom. Okay, the lone pair availability on this N atom is very poor due to resonance. Okay, due to resonance, this lone pair gets delocalized into the benzene ring. That's why this nitrogen cannot donate its lone pair electrons to others. So if someone question you that between methyl amine and aniline, which one is more basic, first of all you have to say that both methylamine and aniline are nitrogenous bases. Nitrogenous bases means that in both the cases nitrogen has lone pair electrons and their basic strength depends upon how easily they can donate their lone pair electrons to others. Now in methylamine, due to the plus I inductive effect of methyl group, plus I effect means bond pair repelling effect, it repels the bond pair electrons towards the nitrogen atom, so the electron density on nitrogen atom is increased, so the lone pair availability also, now if it has more, it can donate more nitrogen, so this nitrogen can easily donate its lone pair electrons to others. On the other hand, in case of aniline, the nitrogen, the lone pair of nitrogen, this sentence must be used, the lone pair of nitrogen is in conjugation with the pi electrons of benzene. I repeat, the lone pair of nitrogen is in conjugation with the pi electrons of benzene. That's why the lone pair can easily get delocalized into the benzene ring through resonance. Okay, you can see this lone pair is surrounding the benzene ring in form of a negative charge. So the lone pair is delocalized into the benzene ring through resonance, the lone pair availability is decreased, so the basic strength also. Okay, now the next question is, this one was a question number 1 between methylamine and aniline, which one is more basic. Question number 2, now arrange the following compounds in order of their increasing basic strength in gaseous phase, in gas phase as well as in aqueous solution. So question number 2 is CH3NH2, CH3 whole twice NH and CH3 thrice N, that is methylamine, dimethylamine and trimethylamine. Arrange these compounds in order of their increasing basic strength in gas phase as well as in aqueous solution. Now first we discuss what will happen in gas phase. In gas phase, the basic strength of a nitrogenous base depends only upon their tendency to donate lone pair electrons to others. All these molecules are nitrogenous bases, as in all the cases NH2 group is present and nitrogen is carrying a lone pair electrons. So in all the cases this nitrogen can donate its lone pair electrons to others. All are nitrogenous bases, but basic strength depends upon their tendency to donate the lone pair electrons to others. If they have more, they can donate more. This is the basic rule. If you have more, you can donate more. Here only one CH3 group is present, and you can know what is, as you know that CH3 group has plus I inductive effect. That means electron pair repelling effect. So CH3 repel its bond pair electrons towards its nitrogen atom, making its electron density more. Here two CH3 groups are present which are repelling electron pairs towards the nitrogen atom from both the sides, and here three CH3 groups are present. They are repelling the bond pair electrons on nitrogen atom. So where will be the electron density? Most electron dense nitrogen will be this one. Okay, so lone pair giving tendency will be maximum on trimethylamine due to the presence of three CH3 group, which will show their plus I inductive effect and which will increase the electron density on nitrogen atom most. Okay, here three methyl groups, here two, here one. So electron density on nitrogen atom will be increased most in trimethylamine, then dimethylamine, then methylamine. So the basic strength, increasing basic strength means from smaller to higher. So this one will be the smallest, this will have the smallest electron density, smallest tendency to donate lone pair electrons, as only one CH3 group is there, and this one will have lesser electron density on nitrogen atom as two CH3 present, and this one will have the most electron density on nitrogen atom as three CH3 groups are present. So the basic strength is this one the first, this one is second, and this one is the third. That is the electron density. This is the order of basic strength. This is the order of basic strength of this nitrogenous bases in gas phase. Okay. So now let us consider the order of these compounds, the order of basic strength of these compounds in aqueous solution. What happens in aqueous solution? Okay, listen carefully. In aqueous solution, the basic strength of a nitrogenous base depends not only upon their tendency to donate lone pair electrons to others, but also depends upon the stability of the cation so formed by uptake of proton from water molecules. Why ammonia? First the question is, why ammonia is an Arrhenius base? Why should we say ammonia as an Arrhenius base? Because we know Arrhenius bases are those which can give OH minus ion or hydroxyl ion in aqueous solution. In NH3 molecule there is no OH group at all. So how can we say ammonia is an Arrhenius base? This is because when you dissolve ammonia in water, H2O dissociates into H plus and OH minus ion. Now ammonia, NH3 nitrogen has lone pair electrons, so it can donate its lone pair electrons to this H plus ion. Hydrogen ion has a vacant 1s orbital, so a coordinate bond can be made between NH3 and H plus to form NH4 plus ion. So ammonia actually abstracts H plus ion from water molecules and remains, OH minus ion remains free. That's why we can see an excess amount of OH minus ion in aqueous solution of ammonia. That's why we get excess amount of OH minus ion in aqueous solution of ammonia. That's why ammonia is called base. Okay, so here the same thing happens when these nitrogenous bases are dissolved in water. They actually abstract H plus ion from water, making OH minus ions free. That's why all are Arrhenius bases. So CH3NH2, CH3NH2 will abstract a proton from H2O molecules to form CH3NH3 plus ion. Here two hydrogen atoms are already present in CH3NH2. Now when another H plus comes from H2O, so this cation is formed, okay, where nitrogen is carrying a positive charge. Similarly, when this molecule CH3 whole twice NH, CH3 whole twice NH is present, it can also accept one H plus from water to form this cation, And when these molecules, in case of these molecules, 3 CH3 groups are there. In trimethylamine, 3 CH3 groups are present. When it abstract H plus ion, this cation is formed. Okay, now we have to consider the stability of this cation in aqueous solution. More stable the cation in aqueous solution, more tendency, it will have more tendency to form this. Now to form this, it will abstract more and more H plus ion and making the excess OH minus ion in aqueous solution. So stability, how can you consider the stability of this cation? In aqueous solution, stability depends upon the solubility. More soluble, more stable. Solubility of water, solubility in water depends upon the extent of hydrogen bonding. More number of hydrogen bonding, more will be the solubility, more the solubility, more the stability. Okay, here 3 hydrogen atoms are there, so 3 H2O molecules can make hydrogen bonding. So it will be surrounded by 3 H2O molecules via hydrogen bonding. So this one is most soluble in water. Here 2 hydrogen atoms are present, 2 H2O molecules can make hydrogen bonding. So it is less soluble than the previous one, and these molecules here only 1 hydrogen atoms are present, so it is least soluble. So this one is most soluble, so this one is most basic in aqueous solution, then this, then this. Okay, so repeat again, in aqueous solution the solubility of a nitrogenous base depends not only upon their tendency to donate lone pair electrons, but also the stability of the cation so formed by uptake of proton. Again, the stability of the cation depends upon the extent of hydrogen bonding. More number of hydrogen atoms attached to the molecules of the cation, more will be its solubility, more will be its solubility, and more will be its stability also. Okay, so more number of hydrogen atoms are present, more will be its basic strength. Just converse or reverse to the order is just reverse to the order in gas phase. In gas phase, number of methyl groups are more, basic strengths more, but here the number of hydrogen present more, basic strength will be more. Now let us consider some reactions of amines. Let us see the conversion from benzene to aniline. From benzene to aniline. Now, how can you convert it? First take benzene to nitrobenzene. To get this, we need to add concentrate, we need to give a mixture of concentrate HNO3 plus H2SO4 and maintaining the temperature maintaining the temperature from 50 to 60 degrees centigrade. Okay, where nitrobenzene will be formed. NO2. Now, if we reduce NO2 by using tin and concentrated HCl, SN and concentrated HCl, then we will get aniline. Okay. An important reaction in amines is diazotization reaction, when aniline is treated with a mixture of sodium nitrite NaNO2 and dilute HCl, maintaining a temperature of 0 to 5 degrees centigrade. Diazonium chloride is formed, benzene, and here N2 plus Cl minus. This compound is named as diazonium chloride or diazonium salt. Now, once diazonium chloride is formed, we can make so many conversions. Okay. Here if N2 plus Cl minus ion is formed, then according to Sandmeyer reaction, If you give CuCl with HCl, you will get chlorobenzene. If you give CuBr and HBr, you will get bromobenzene and so on. So let's look at those reactions. Diazonium chloride. This one is diazonium chloride, N2 plus Cl minus, Sandmeyer reaction, CuCl, HCl, and you get chlorobenzene. CuBr, HBr, you get bromobenzene, CuiHi, iodobenzene, CuCN, KCN, you get cyanobenzene, Now if you give CuCN and KCN, you will get cyanobenzene. If you give just aqueous solution of the acid, that is H3O plus, you will get phenol. If you just heat it by H3PO2, then you will get benzene. If you give HBF4, you will get fluorobenzene. If you give sodium nitrate, a mixture of sodium nitrate and potassium nitrite, you will get nitrobenzene. So here is the chart, and if you follow this, you can solve all the conversion problems. Okay, you just need to write down this chart. First, these three reactions or these four reactions, CuCl, HCl, similar reactions are there. CuCl, HCl in diazonium chloride gives chlorobenzene. CuBr, HBr, diazonium chloride gives bromobenzene. CuiHi, diazonium chloride gives iodobenzene, and CuCN, KCN in diazonium chloride gives cyanobenzene. These four reactions are called Sandmeyer reactions, and this reaction is called Schumann reactions. Okay, so this chart is very helpful to you, I think. Now according to this, I will make some conversions in my next class.